All right, guys, so we're talking about limits today. Limits are interesting. I'll tell you what they are in just a sec. This is Unit 1 of Calculus, just so you know. It's our last unit. It's also Unit 1 of Calculus. A limit, I'm not going to give you like the official crazy definition because it's a little confusing. I'm going to tell you more what it is. A limit is the y-coordinate or value that a function approaches and that word approaches is really important. As x approaches a given number. And something that's really important is so the difference between the y-coordinate that a function approaches versus the y-coordinate that might actually be there might be different. So what we'll say is it's not necessarily the actual y-coordinate of the function. Let's get your seats up there. Okay. So we've seen limit notation before when we were talking about end behavior. We were talking about x approaching infinity. Now we're talking about x approaching any number. We've got some sort of interesting notation here, and I'll come back to this and it'll make a little more sense once we see some examples, as always. The way that we would say this is the limit of f of x as x approaches a from the right. That's what that little plus is telling us, from the right. So it's like from the positive direction. And the other one's very similar. Your seat is right there. Here, grab one of these two. Okay. Sometimes these are abbreviated. The right-hand limit and the left-hand limit. I didn't choose red and blue for political reasons. I was choosing red for right because it starts with R, but maybe that's why the right side chose red as their color. Red for right, I don't know. Anyways.
Really bring politics into math class?
I'm bringing it in. No, I didn't mean to. That's my whole point. I didn't mean to. limit as x approaches a with no plus or minus. This is refers to approaching from both sides. So we don't have to write out the whole thing. This is the limit from both sides, like together. Or both directions. Bipartisan. All right, so we have a relationship between limits existing and continuity that I'm gonna come back to once we do an example here. So today we're looking at limits from graphs. This is the easiest way of finding limits, is just if you can look at the graph and see what the value is approaching. So I'll show you guys how this works. Again, it's all about the function, the value that we're approaching, not necessarily the actual y coordinate. So here's number one. As we approach x equals 3, we can approach 3, 1 and 2 from the right and from the left. As x approaches 3 from the right, our function is going like this. And we are approaching that y coordinate right there. There's an open circle, but that's the y coordinate we're approaching as we come in from the right side, from the positive direction. As we come in from the negative direction from the left side, so it's like, think about our x's. Our x's are moving from the left side and from the right. We're approaching 3. The y coordinate that we are approaching is 2. So you can almost think of a limit as like, one of the literal meanings of limit is like the edge of something. Like the limit of your knowledge is like the edge of your knowledge, or the limit of a like a field or something like that is the edge of the field, or the boundary lines, whatever. So you can think of this as like, as we approach from the right, like what's the edge of the path right here? What's the very end? What's the last place we can get to? It's that y coordinate right there. It's 3. So even though there's an open circle. Okay, so notice how the left-hand limit and the right-hand limit are not the same. And what we can see there is that happens when we have a jump discontinuity. When the left-hand limit and the right-hand limit are not the same, we say the limit from both sides does not exist. The limit does not exist. So there's your Mean Girls quote.
Rather than undefined.
Yes, exactly. Exactly. It's different than undefined. So undefined, and this is an actual difference that matters, and I take points off all the time in calculus because of this. Yeah. So undefined is refers to the actual value of the function. Like the actual y coordinate, like if you have a vertical asymptote where the y coordinate is just missing, it would be undefined. Does not exist refers to limits. And limits only. So something I'm going to write up here under this this one here is a limit does not exist when, I'll abbreviate here, the right hand limit does not equal the left hand limit. L's looking crazy, sorry. So inversely, a limit exists only when the right-hand limit equals the left-hand limit. Okay, so we'll do some more examples here, but you guys will very quickly get the hang of this. This is not that hard of a topic. It's just the y-coordinate that the function's approaching. We'll see some weird kind of rules and exceptions here, but that's kind of the idea. So as we approach, so 4, 5, 6 are talking about as we approach 1, x equals 1. So that's right there. What we can see is as we approach from the right, from the left, remember that's like in terms of the x values, approaching from the right, from the left, we do get to the same point on both sides. The point is 1. It also happens to be the y-coordinate there of the function. As we approach 1, the y-coordinate is 0. And the y-coordinate that we're approaching is 0. And so if the left-hand limit and the right-hand limit are the same, then the limit from both sides is that same number. You guys do 7, 8, 9. Why was 6 afraid of 7? Because 7, 8, 9.
So there's continuities that makes it so that the limit does not exist.
Jump discontinuity and infinite discontinuity.
Thank you.
Yes. Okay, turn to your neighbor. What'd you get for 7, 8, and 9? Okay, so there's x equals 2. As we approach from the right and from the left, notice that we are approaching the same y-coordinate. We're approaching y equals 1 from both sides, and that is the limit from the left, from the right, this is from the right, this is from the left. And if the left and right are equal, then the limit from both sides is that number. And so what we're going to see is that if a function is continuous at a point, then the limit always exists at that point. So we'll come back up here and write that. If a function is continuous at x equals a, then the limit always exists at x equals a. When we look at as x approaches -1, notice at x equals -1 our function is continuous, so our limit is 0. And as x approaches -2, our function is continuous, and so our limit is -1. Actually, the definition of continuity, which we'll talk about in a few classes, is that the limit and the y-coordinate are the same number. Warren. Your new seat is back there next to Ben. Here you go. Okay. Now, let's look at, well, you guys do 12, 13, 14. All right, so we're looking here at x equals -3. You can see there's a jump discontinuity based on what we saw at x equals 3, that like the limit is not going to exist here. But as we approach from the right, what is our limit? 0. As we approach from the left, what is our limit? 2. So notice how, like, approaching from the right doesn't necessarily mean this whole journey here all the way there. It's like really just the points that are just to the right of this. Like as we get like really, really close, like right here, what are we going towards? It's x equals 0. So you don't need to start like all the way back here. Long epic journey. You can. I mean, it's like, you know, the limit of Frodo's destination is Mount Doom, the pits of doom. But, you know, that's the limit of his journey, whether you start keeping track in Mordor or you start keeping track like at the doorway to the mountain or you start keeping track back in the Shire. It's the same limit no matter what. So there's the metaphor. If you haven't seen Lord of the Rings, you should become cultured. But anyways, that's my metaphor. So from the right, 0. From the left, 2. But if those two limits don't match, we always say what?
Does not exist.
Does not exist, exactly. And just to be picky here, because I'm a calculus teacher and we're picky, you don't say equals does not exist. Think about reading it out loud. The limit of f of x as x approaches negative 3 does not exist. But for 12, we would say the limit as the limit of f of x as x approaches negative 3 from the right is 0 or equals 0. So that's just to be a little picky. Okay. Here's where limits get slightly more confusing, or here's what makes them different. As we look at approaching 0, as x approaches 0, which is right here, you notice we have a hole in the graph. But what y coordinate do both sides of this graph approach? 2. So the limit exists and is 2. This is the situation that makes limits different from everything else we've learned. Like the limit's just 2. Even if we don't actually get there, the limit is 2.
So whether it's a hole or not, it doesn't matter.
Correct. Yeah. As long as both sides approach the same value. And this is true even if, let's just put another point in here for fun. Take your pencil and draw a point there at x equals 0. So we've seen a bunch of graphs like this on our homework, right? Where like we're approaching, the function has a hole and then there's like a random point somewhere else at that x coordinate. Nothing changes about the answers that we wrote. The limit is still 2. We're headed towards 2. It's okay that we didn't get there. That was the edge of our path. It was the very end of our journey, was 2. And the only thing that I would throw in here is if I wrote number 18 and I wrote f of 0, turn to your neighbor, what does f of 0 equal?
1.
F of 0 is 1. Yeah, it's where the actual y coordinate is. In numbers 1, 2, and 3, we were looking at this jump discontinuity. We saw the limits from both sides. 3, 2, the limit does not exist. What if I ask you, what is f of 3? What does f of 3 equal? Two. Yeah. What's the actual y coordinate there? It's 2. What is another limit that we saw did not exist was negative 3. What is f of negative 3? 0. Yeah. We just picked the point where the closed circle is. So that's the difference between the limit and the y coordinate. So to finish off our notes on this page, on this side of the page here. So if a function is continuous at x equals a, the limit always exists. If the limit exists at x equals a, so going in reverse, the function is not necessarily continuous at x equals a. So our Venn diagram here that represents this logical situation is, we would say the limit exists at x equals a, and the function is continuous at x equals a. So if a function is continuous, then the limit exists. but it doesn't work in reverse. All squares are rectangles, not all rectangles are squares. Okay, let's go to the back. I want you guys to do these problems right there. Ready, set, go. This is not too bad, right? Okay. What'd you guys get for numbers 1, 2, and 3? 2. Yeah. The function is continuous, which means the limit and the y-coordinate will be the same thing. They all approach 2. Great. Let's see. As we approach 1 from the right, what do we get? 1. 1 from the left? Which automatically means number 6. Yeah. Does not exist. Okay. The limit at -1 is -2, and the limit at -2 does not exist. So we have the two sides are different. So a limit never exists at a jump discontinuity. Let's say limit always DNE at a jump discontinuity. Because basically what we're saying is the left-hand limit does not equal the right-hand limit. That's always true at a jump discontinuity. That's actually the definition of a jump discontinuity. I'm basically spoiling our whole lesson on continuity right now. May 13th will be easy. Okay. In this graph here, the only difference is now instead of numbers we have letters. That's just math, right? The more we do, the more we swap out the numbers for the letters, right? You guys have probably noticed that. There's a couple different things that we're doing here that I want you to notice. We've done this before. The limit as a function approaches infinity, as x approaches infinity. So as we approach infinity, you see how what y-coordinate we're approaching there? F, yeah. It's written in a weird place, but it's supposed to be F. It's the same as the horizontal asymptote. Which does appear to be the same limit as we approach negative infinity, although it's a little hard to tell. We'll just say it's F. Okay. But now we're talking about approaching A from the right. You see we have a vertical asymptote there. There's actually a couple ways we can answer this. So what are we approaching as we come towards A from the right? How can we describe that? Well, we have a vertical asymptote, but like what are the y-coordinates approaching? Infinity. So we can say that we're approaching infinity, which is true. But that being said, here's another way to think of it, and both are correct. if the number that we're approaching is infinity, would you say that there is a limit to the y values that we can achieve? No, there's no limit. So we can also say the limit does not exist. And both are correct. And actually, they're both so correct that this year in pre-calculus, what we want you guys to do is say both. We want you to say infinity, comma, does not exist. Because there are two ways of thinking about it. Infinity tells us that we are going upward in a positive direction forever, so that's helpful. It's helpful to know which direction the function is headed. Because it could be negative infinity does not exist, or it could be because the function just doesn't even go over there, which it does. So we're going to say both. Infinity does not exist. Next year in calculus, the answer that you're going to say is just dne. You're not even going to worry about the infinity, but not this year. As we approach a from the left, we see we're approaching h. Okay, do the rest of these. Ready, set, go. All right. So the limit as we approach a for number 5 is does not exist. Yeah. So since left and right hand are not equal. Okay. As we approach b from the right. Yeah. B from the left. B overall. B from both sides. Okay. As x approaches c. What we say? X approaches c. 0. Yeah, right there. So the function's continuous there. Right there on the axis, so 0. As x approaches d, 0. G of a. This is where we would say undefined. So undefined when we're talking about location of y coordinates. Like the actual y coordinate. Not the limit. So undefined for functions, dne for limits. It's picky, but math is picky. It matters. You know, 2 plus 2, 2 minus 2. The difference is that, right? But it matters. Everything matters. G of b. I. Yeah, it's that guy right there. G of 0. Also I. The limit at 0. I. Yeah, function's continuous. There. Nice. Okay. So once you get the hang of it, limits from graphs are very straightforward. You just got to look and see what we're approaching. Limits do get more difficult. They will get more difficult next class when we start looking at equations of functions when we can't actually see the graph. Because we're going to run into some situations where we can't. It's a little hard to figure out what the limit is, and we have to do a little fun analysis. But that's kind of the general idea. So it's not too bad. What we're going to do